続きまして、本日の招待講演をご紹介申し上げます。D-Wave Systems CFO ダン・コアース様から、プラクティカル・クォンタム・コンピューティングと題しました招待講演を賜ります。It is my honor to introduce the invited speaker, Dr. Dan Cohrs of D-Wave Systems. Let's welcome Dr. Cohrs.
ありがとうございました。すみません、日本語ができません。So I will switch to English because that's all my Japanese. But I'd like to thank the organizers of this conference and also thank the previous speakers because both of you have made my job much easier in terms of explaining some of the things that I need to explain. But thank you for inviting me. I'm very happy to be here in Tokyo, which was, of course, the birthplace of quantum annealing. We just heard from Professor Nishimori and Professor Orawaki essentially gave birth here in Japan to quantum annealing. And the next year, this paper was published in 1998. The very next year, in 1999, D-Wave Systems was founded by two physicists at the University of British Columbia. For the next 5 years, they simply studied the technology. They studied quantum annealing, they studied gate model, and they met some people who were engineers working at TRW, which became part of Northrop Grumman, who were the world's greatest experts in building superconducting circuits. And in fact, they still are the world's greatest experts in building superconducting circuits, and they work at D-Wave Systems. So in 2004, the original founders of D-Wave decided to start building quantum annealing devices because they thought that would be the best way to become commercial as quickly as possible. Now, this is 15 years ago. So today, we have essentially a very robust teenager. This system, in some sense, is 15 years old. This is our current generation of the technology, the D-Wave 2000Q. It has 2,000 annealing qubits. It's become large, it's become very powerful, and yet it's not quite really an adult yet. It's performing some things that are very difficult for adults to do, but we're not quite there yet. So I'd like to talk about where we are, what's happening in Japan, because as Japan was the birthplace of quantum annealing, it is still perhaps the best market for us in quantum annealing. There's more activity in Japan, I think, than anywhere else in the world. So let's talk about that. Talk about how D-Wave fits into the world of quantum computing, and then talk a little bit more about how we're making a business from quantum computing and quantum annealing. First, let's talk about, I'll just give you some examples about what's happening in Japan. There's so much activity in Japan that I can't even describe to you all of it. So I'm going to pick a few examples, and I apologize to some of our customers who I might have to leave out here because we have a lot of customers in Japan. This is just a summary of, there are 9 projects here that have been developed at Tohoku University with Professor Ozeki and some of his colleagues and also collaborators. So we see problems solved in things like transportation optimization, optimization of factory, optimizing the operations of factories, portfolio optimizations for financial securities with people like Nomura Securities, partnering with companies like Kyocera and Denso. So a huge amount of activity focused not only at Tohoku, but also at Waseda University and Tokyo Tech and other parts of the ecosystem that's developing in Japan. In fact, Professor Ozeki has recently formed a new company called Sigma I to collect some of this activity and promote it and promote the development of this ecosystem, which is doing so much wonderful work in Japan at developing applications. A customer called GrooveKnots has just launched the first system, the first service available to customers that incorporates a quantum computer. This is a huge event in the history of D-Wave. So essentially, this is actually very similar to the problem we heard earlier about the call center. This particular application is about how to optimally restock vending machines in Japan. So the first step is GrooveNaut's basic business is to provide machine learning predictions. Now, we have a prediction from a machine learning model. What do we do with it? We need to add to this an optimization routine. So we now have a prediction of when the vending machine needs to be restocked. Now we need to create an optimal routing for the trucks. Now, I think we all know this is a very difficult problem. And so you can see the architecture diagram at the top. We've now plugged in a D-Wave system, which is accessed remotely over the cloud, to provide the optimization. GrooveNauts, by the way, has also developed call center optimizations, very much like the example we heard about earlier. So a lot of great work going on here in Japan. There are more examples here. And if we look worldwide with all of D-Wave's customers, we have more than 150 examples like this. We call them early applications because they are not yet quite large enough problems to really stump all of the classical computers. Classical computers can still do these calculations, but they're very real problems, and they're very important problems, and they cover a broad range of scientific and commercial applications. You can see companies like Denso, we talked about GrooveNauts. Recruit Communications is doing work on optimizing web advertising, the pricing of ads on the web, as well as the display of search results. They've done an application where we display search results in a hotel reservation system and actually show that we can increase revenue by the way we optimize the display of those results. We talked about Nomura Securities. And again, this is only a sample of what's happening here in Japan. MDR is working with 20 different clients in a broad range of industries on applications like portfolio optimization and risk management with MUFG Bank. So a lot of activity. This is, again, a relatively small sample of our customers, many of which are in Japan, and you can see many of the names of our Japanese customers here. But in total, we have 3 systems installed with customers. So Lockheed and USC, University of Southern California, share a system. Google and NASA share a system, which is installed at the NASA Ames Research Center. The Los Alamos National Laboratory has its own system. So those are our 3 systems installed at customer centers. But in a way, even more importantly, we have more than 40 customers now who actively access these systems over the web. I'll talk more about how we've made this very easy later. And in addition to those 40 customers accessing over the web, over the cloud, there are another 40 or so users that access our systems and use them through programs at NASA and Los Alamos and even at Oak Ridge National Lab, who is another cloud customer for us. So again, we have today with us 1Qubit, who is part of this developing ecosystem, writing software for quantum computers and developing applications. There's a lot of work going on, and some of the best work is going on right here in Japan. If you want to learn more about these 150 applications, these are all contained in presentations that have been made at our user group meetings. Twice per year, we get our users together at conferences so they can discuss and make presentations, and the links are on this slide. I think these slides will become available so you can actually go to our website and study all of these 150 applications. Let's shift to talking a little more about quantum computing and where we think we stand. This is some of the themes that Professor Nishimori talked about. The National Laboratory in Germany at Jülich has studied quantum computing. There's a supercomputing center there, and they've done the best they can to evaluate the available quantum computers, and they've created a technology readiness level. At level 1, it's pure theory. Richard Feynman has just invented the theory of quantum computing. And this goes up to level 9. At level 9, we would be outperforming all of the best classical computers using the best classical algorithms. So let's see where they ranked a few people. Some experimental devices are at 4. Well, we got out of order there. IBM and Google and Rigetti are at 5, D-Wave is at 8. We think this is actually quite a fair ranking of where we are. We are not quite yet at the point where on real problems we're outperforming the best classical computers. We'll come back to that in a second. I think it's very important to note, this is back to Professor Nishimori's point, that here, in order to move from level 5 to level 6 is going to take a long time, because today these devices are roughly on the size of 20 qubits. In order to get to level 6, they need to implement error correction. And in order to implement error correction, they need millions of qubits. This will take a long time. Let's see how that's been going so far. We have a history chart here. Notice it's on a log scale, so these are really exponential growth curves. But in the history of the gate model community, they've gone from 9 qubits to 20 qubits that we're sure actually work. There's been, Google has manufactured a device with 72 qubits, but there's no data, so we really don't know the performance characteristics. In the same time frame, D-Wave has gone from 0 to 2,000, and we've announced that in the middle of 2020, we'll have a chip with more than 5,000 qubits. So what we've shown is that scaling in annealing has been much easier than scaling in gate model. What people are starting to really learn is that scaling, especially scaling to millions of qubits, is an extraordinarily difficult task, and it's going to take a long time. In fact, Google itself has published a chart that says in order to have a useful error-corrected gate model quantum computer, not only do we need millions of qubits, but we need to reduce the error rate by about a factor of 100. So the qubits have to become 100 times better, and we have to go from 20 qubits or 72 qubits to millions of qubits in order to really have a useful device. It's extraordinarily difficult. Now, annealing qubits and gate model qubits are not the same. And of course, many people talk about this. It's a long academic discussion to try to figure this out in theory, but we now have examples where we can actually compare the results of a state-of-the-art gate model system and a state-of-the-art annealing system produced by D-Wave. Rigetti Computing published the solution of a problem on their 19-qubit device. So our engineers programmed the same problem into the D-Wave system. Notice when Rigetti solves the problem, they have to run it about 100,000 times to get one answer, because this is not an error-corrected device. It only has 19 qubits. When we programmed the system into our D-Wave device, we got answers every time. So every run, we get the answer. And in addition, we could put 102 copies of the problem into our device. So every time we ran it, we actually got 102 answers. So in some sense, we're 10 million times better than a state-of-the-art gate model device on the same problem. Actually, Professor Nishimori talked about this. There are many large entities with lots of money trying to pursue gate model computing because it's so theoretically appealing. But we've also talked about how difficult it is. So let's focus for a second on annealing and talk about what D-Wave does in annealing. As I mentioned at the beginning, the founders of D-Wave were really aerospace engineers. Some of the people who came from Northrop Grumman had been producing devices. So from the very beginning, they thought about how will we build a quantum computer that we can manufacture and that we can scale and that we can actually produce at a reasonable cost. So that was part of their thinking. These were not just academic physicists trying to develop machines that would do certain algorithms. And so they built this quantum computer. This is sorry about that. This is the processor here, about the size of your fingernail. It's produced as a standard silicon chip with special materials and special processes. This is one cell. This contains 8 qubits, and we have 2 qubits outlined here. And this, of course, is what it looks like when it hangs inside that machine. Now, many of you are quantum annealing experts, so you know this equation. What this tells us is that if we can write down the problem in an equation like this, we can solve it. We can program that equation into our device by inserting values for these coefficients into the device. We program the problem into the device, and then we simply let it relax. It finds the lowest energy state in a few milliseconds. That's why this system works. It's finding the lowest energy state. In contrast, gate model systems must create essentially a high energy state. They have to create a very difficult quantum state of coherence and maintain it long enough to complete their sequential calculations. That's a very difficult problem. This is a fundamentally easier way to compute. And notice, this is a fully programmable device. It's not limited purpose in that sense. It's fully programmable, and it can solve. I'm sorry, I have to get the pointer going. It can solve any classical problem. In principle, we can write any classical problem in this form. Now, nevertheless, as a quantum computer, it's somewhat limited. We can't solve every quantum problem. But what we have done, this is actually another chart that Professor Nishimori previewed here. We have built a small device already that takes us an important step towards building a universal quantum computer that can handle any quantum calculation. What we've done is build this device, small 2-qubit device, that adds these two terms to that equation. And by adding those two terms, we can program more complicated problems, capture more quantum effects, and that's why we think this is a very important step towards actually building a universal quantum annealer. We're thinking now about 2 generations ahead in order to start building a universal quantum annealer. But once we do that, this is mathematically equivalent to a scaled gate model computer. And so this is the path we're on. In terms of where we are today, we've already shown that we can solve very sophisticated problems with the device we make today, our D-Wave 2000Q. We published papers last summer in Science and Nature. Just for example, Ned Allen, the chief scientist at Lockheed, said this is the first useful thing anyone ever done with a quantum computer. And these were remarkably sophisticated problems, and yet they could still be done by classical computers. Now, in order to make a business from this, it's not enough that we're 10 or 15 years ahead of the rest of the gate model computing world. The quantum computing world is probably 10 or 15 years behind us. What we need to do is outperform classical computers. On benchmark problems, on synthetic benchmark problems that are not real problems, it's now been proven that we can outperform the best classical computers and the best algorithms. Now, but these are not useful commercial or scientific problems. They're very difficult problems. They're becoming close to real physics problems. What we really want for a business, though, is for these customer problems to move up in that direction. We are getting close. This is the most recent example. You can read the quote. It says that on the D-Wave system, we're starting to see results that are about as good, sometimes better, than the classical alternative on these problems. Now, these types of examples are starting to appear. Out of the 150 applications, there are probably 2 or 3 dozen that have statements like this. We're getting very close to outperforming on real customer problems. So now our job is to keep moving in this direction. How will we do that? In simple terms, we keep building more powerful systems, and we also make them easier to use. We'll build more powerful systems, just as we've done for the last 15 years, by adding more qubits. But perhaps just as important, we will add more connectivity in the qubits, reduce the noise, improve the annealing features, all of which can substantially improve the performance. And so we're now building the next generation, and we're looking 2 or 3 generations out. It's very important to make these things easier to use, because that way we can get thousands of people, not just hundreds, using quantum annealers who can come up with more and more applications and creative ideas for how to use them. And sometimes the software tools are important for improving performance too. Essentially, through software, We can do things like break hard problems into smaller pieces, and we can solve the smaller pieces or find the hardest part of the problem and let the quantum computer solve the hardest part of the problem and let other computers, classical computers, solve the rest. This is a sketch of our next generation quantum system, which is due mid-2020. We've announced this recently. It will have more qubits, 5,000 versus 2,000. Each qubit will be connected to 15 other qubits rather than 6, and we'll have about a 5 times reduction in noise, which at least on certain problems improves performance by about 25 times. Hyperion research says that this architecture, the Pegasus architecture, will be the key to making quantum computers useful for real applications, and we agree. We've made this system available over the cloud. Last October, we launched a service called LEAP, and it's a real-time access to a quantum computer. Anyone can do it. We charge about 300,000 yen per hour. We give away small free samples so you can try it out and decide if you want to buy more, but this is now available with a tremendous amount of resources to learn how to use the system. We continue to work on our software stack, so it's now possible to operate on a D-Wave quantum computer if you're comfortable in Python or C+. You don't really have to worry about that complicated cubo form of equation. You can operate on this if you're more like a standard software developer and you program in Python. We definitely see hybrid systems. We're working on hybrid architectures already. We see delivering this through the cloud, and we see just as a CPU and a GPU work together today, in the future, we'll have CPUs, GPUs, FPGAs, quantum processors in data centers working together. What we need for that will be software to manage those hybrid workflows. Well, we've already made the software available. This is open source software. We open source all of our tools, but we already now have the open source software available to start to manage these hybrid workflows. And so we're definitely moving in this direction where the quantum computer solves the hardest part of the problem, the classical computer solves other parts of the problem that classical computers are good at. So this is a business conference, so let me spend 1 second talking about D-Wave as a business. We have the 150 early applications. We sell, lease, and provide cloud services to quantum computers. We provide custom fabrication of superconducting devices. We provide machine learning services. We're looking for investors and customers because we're not yet cash flow positive. So if you're an investor, talk to me. If you're a customer, talk to Janai-san and Nomoto-san, who are here with me today. I think it's remarkable that our customers have put down $75 million of sales contracts to essentially experiment. You know, these are not yet really commercial devices, as we've talked about. I don't know of another example in the history of technology where customers have signed up for $75 million worth of contracts to run experiments so they can learn how to use these systems in the future. And I think we're just about out of time. Thank you very much. Arigatou gozaimashita.
Thank you very much, Dr. Cohrs.